So this is my second time today to do this rather lengthy video because the first time I didn't know my microphone wasn't working. In section 2.4 we're going to talk about real zeros of polynomial functions, and this is something that you did last year in Honors Algebra 2. So when you divide a polynomial f of x by a divisor d of x, you get a quotient polynomial q of x and a remainder polynomial r of x. So what we're going to do is we're going to talk about how to divide polynomials using long division and how to divide polynomials using synthetic division. So our first example, divide 2x squared plus 13x minus 7 by x plus 6. Now that expression is basically the same thing as writing a fraction with 2x squared plus 13x minus 7 in the numerator over x plus 6 in the denominator, or you can write it in polynomial form like this: the quantity 2x squared plus 13x minus 7 divided by the quantity x plus 6. Now if we're going to do long division on this, we're going to write it as x plus 6, and that's going into 2x squared plus 13x minus 7. Now we have a second degree, a first degree, and a constant, and if we had been missing any one of those terms, we would have needed to put a placeholder in there for that place. Anyway, x plus 6, x will go into 2x squared 2x times. So now we're going to multiply 2x times x, which is 2x squared, and 2x times 6, which is plus 12x. And just like when you do long division, you're going to subtract that entire binomial from those upper terms. So we end up with 13x minus 12x is x, and now we're going to bring down the negative 7. And we're going to say the lead term x will go into x one time. 1 times x is x, and 1 times 6 is 6, and we're going to subtract that entire binomial. So negative 7 minus 6 is negative 13, and that is our remainder. So we would write the answer to this as the quotient 2x plus 1, because this is our quotient, minus 13 over x plus 6, or our divisor. So I want you to pause the video right now, and I want you to do this example. And I want you to do it on your own, and then when everybody's ready, start the video again and see if you did it right. So pause. Now that you've started it again, so we have y squared minus y plus 1 will go into y to the 4th. This is where you have to be sure you put in a placeholder because we don't have a cubic term. So we're going to put plus 0y cubed plus 2y squared minus y plus 5. And now it will align okay. So y squared times what gives you y to the 4th? It's going to be y squared for our lead term. Y squared times y squared is y to the 4th. Y squared times negative y is minus y cubed. Y squared times 1 is plus y squared. And we're subtracting this entire trinomial from those upper terms. So 0y cubed minus a negative y cubed gives us positive y cubed. 2y squared minus y squared gives us plus y squared. And now we're going to bring down the negative y. So let's look at our lead term. Y squared times what gives us y cubed? That's going to be plus y. Y times y squared is y to the 3rd. Y times negative y is minus y squared. Y times 1 is plus y. And we're subtracting. Y squared minus a negative y squared is 2y squared. Negative y minus y is minus 2y. And now we're going to bring down the 5. And lastly, y squared times what gives us 2y squared? It's going to be plus 2. 2 times y squared is 2y squared. 2 times negative y is minus 2y. 2 times 1 is plus 2, and we subtract all of that, so 5 minus 2 gives us 3, and that is our remainder. So the final answer on this would be the quotient y squared plus y plus 2 plus the remainder 3 over the divisor, y squared minus y plus 1. That would be your final answer. So dividing polynomials using synthetic division, this is the shortcut method for the dividing for long division, and it's way nicer. So if we want to divide by x minus 1, we would think, well, x minus 1 gives us a solution of x equals 1. So we're going to put 1 in a box right here. Now we're just going to use the coefficient of our terms with our degrees in descending order. So we have 1x cubed minus 1x squared minus 2x plus 8 is our constant. I'm going to put a line here. Now again, if they had skipped any of these degrees, we would need to put a 0 in as a placeholder. For instance, if there hadn't been a squared term, we would have a 0 right here representing our x squared. So the first thing you do is simply carry this first term down. So 1 carries down. Now you say this times this, so 1 times 1 is 1, and you add. Negative 1 plus 1 is 0. 1 times 0 is 0. Add again. Negative 2 plus 0 is negative 2. Now you take negative 1 times negative 2 is negative 2, and 8 plus negative 2 is 6, and 6 is your remainder. So what this means is this place here, the first one next to your remainder, is your constant term. Then you have your x term, and then you have your x squared term. So what we have is this would become 1x squared minus 2 would be our quotient, and then plus 6 over x minus 1. And that would be our final answer. So what I want you to do right now is pause the video, and I want you to do examples 4, 5, and 6. And while you're pausing it, when everybody's ready, start it up again, and I will show the solutions to these. So setting this up, we're dividing by x plus 2, and you think about what the solution to that would be. X would be negative 2. So we're going to put negative 2 in a box, and then put our coefficients. So 1x cubed minus 1x squared minus 2x plus 8. So carry down your 1. 2 times 1 is negative 2. Negative 1 plus negative 2 is negative 3. Negative 2 times negative 3 is 6. Negative 2 plus 6 is 4. Negative 2 times 4 is negative 8. And we get a remainder of 0. So our quotient is actually x squared minus 3x plus 4. And no remainder. Example 5. So if x plus 2 is the factor we're looking at, we want to use negative 2 as our root, and then set it up with 1 x cubed negative 3 x squared negative 7 x, and 6 is our constant. So bring down 1. Negative 2 times 1 is negative 2. Negative 3 plus negative 2 is negative 5. Negative 2 times negative 5 is 10. Negative 7 plus 10 is 3. And negative 2 times 3 is negative 6. And again, we have a remainder of 0. So the quotient here, there's our constant, there's our x term, there's x squared. So we're going to have x squared minus 5x plus 3 is our quotient. And the last one you should have done is x minus 4. That would give us a root of 4. We have 1x cubed negative 3x squared, negative 7x, and 6. Carry down your 1. 4 times 1 is 4. That's 1, 4, negative 3, negative 12, negative 6. So we do have a remainder. So this is going to be x squared plus x minus 3 minus 6 over x minus 4. So the remainder theorem says if a polynomial f of x is divided by x minus k, then the remainder is r, or f of k. So these are actually the 4 examples that we just did, and we're going to look back and see where this r, or f of k, is. So we're going to scroll back 4 pages to where we had this problem, x cubed minus x squared minus 2x plus 8 with the factor of x minus 1. And when we divided this, our remainder is always what's left here at the very end. So in this case, our remainder was 6. Or we can say that f of k equals 6. And then in example B, we had no remainder. So we'd say that the remainder is 0, or f of k equals 0. And then in the next example, which was right here, we again had a 0 remainder, or f of k equals 0. And our last example was this one, and we had a remainder of negative 6, or f of k equals negative 6. So what do we know about x minus k if f of k equals 0? Well, if we look back, what that tells us, let's go to one of these where the remainder was 0. We ended up with x squared minus 5x plus 3. And so if we took x squared minus 5x plus 3 times x plus 2, we would get that polynomial that we began with, which was x cubed minus 3x squared minus 7x plus 6. So what it means when there's no remainder is that this x plus 2 is a factor of the polynomial that we're talking about. So factor theorem, a polynomial function f of x has a factor x minus k if and only if f of k, or the remainder, equals 0. So use the factor theorem to determine whether the first polynomial is a factor of the second polynomial. If it's a factor, use the result to find all other factors. So we're going to test this, which means that 3 would be the root. We have 1x cubed minus 1x squared minus 1x minus 15. So bring down the 1. 1 times 3 is 3. That's 2. That's 6. That's 5. So what does that mean? We have a remainder of 0. Therefore, x minus 3 is a factor. And when we factored it, we get x minus 3. What we're left with is this quotient. And that represents x squared plus 2x plus 5. Now we would then see if we can factor this further. And x squared plus 2x plus 5 is not going to be factorable. Now if you want to see if this polynomial would have any solutions, you could set it equal to 0 or set it equal to y and put it into your calculator, and that would tell you if this is going to cross the x-axis anywhere else. But I know that this in and of itself is not factorable. So x plus 1, we're going to test out -1 in this case as our root, and then we'd have 2x to the 10th, -1x to the 9th, 1x to the 8th, 1x to the 7th, 2x to the 6th, 0x to the 5th, 0x to the 4th, 0x to the 3rd, 0x squared, 0x, and -3. Now we're going to see a pattern fairly quickly that's going to tell us if this is a divisor or not. And so let's bring down our 2. -1 times 2 is -2. That gives us -3, 3, 4, -4, -3, 3, 5. Here's where we're going to start seeing a pattern. -1 times 5 is -5. That gives us -5. -1 times -5 is 5. That gives us 5. -1 times 5 is -5. And this is just going to keep going like that. 5, -5. And we could have seen probably back here that this was definitely going to have a remainder of 2. So x plus 1 is not a factor of this polynomial. So using your graphing calculator to determine at least one integer factor of the polynomial function that, and use synthetic or long division to determine the other factors. So I've already put this into my calculator because I didn't want to take time. And so if I look at my y equals, this is under y sub 3, and I've deselected the other two polynomials that I've put in here. So the only one we're going to see when I graph this is this one at hand. Oh, and I need to change my window. Now we're going to have to wait for it to graph.